Good morning and welcome to my presentation about subverting stateful firewalls and protocol states. I'm Klein from the Hebrew University, and this research is part of my PhD thesis in Bar-Ilan University, supervised by Professor Benny Pincus. The research I'm presenting today is about how to exfiltrate data from isolated networks and how to uncover the physical architecture of virtual network services. The first example is firewall piercing, wherein a stateful firewall prevents an isolated network, shown in green at the bottom of the image, from accessing the internet. No packets are allowed to travel from the isolated network to the internet and vice versa. We will show how we can still send bits from the isolated network to the internet through the firewall itself. The second example is firewall subversion, wherein the isolated network is allowed to access a host in a DMZ, which can also be accessed by internet clients. We will show how to send bits from the isolated network to the internet through the DMZ host without violating firewall policies. The third example is firewall subversion via containers, wherein the isolated network container contains a server that runs on a container, which is co-hosted with a container on the internet side. We show how this multi-tenant container environment, sharing the same kernel, can be used to exfiltrate bits from the isolated network to the internet. Finally, in a host alias detection scenario, the attacker determines whether two virtual network services behind the NAT reside on the same physical host or not. The research approach is to construct a covert channel between the sender host on the isolated network and the receiver host on the internet. The sender and receiver communicate indirectly through the pivot host. The sender communicates with the pivot host in one protocol, and the receiver communicates with the pivot host in another protocol, possibly identical to the sender's protocol. To send a single bit, the receiver first polls the pivot host's internal protocol state. This is done by sending one or more packets in a certain protocol, such as ICMP, and extracting the internal state from the pivot host's responses. To signal the bit 1, the sender then sends some packets in order to modify the pivot host's internal state in some prescribed manner. To signal the bit 0, the sender does nothing. Finally, the receiver polls the pivot host again to determine whether the internal state changed in the prescribed manner. If it did, the receiver interprets this as the bit 1. If it did not, the receiver interprets it as the bit 0. We use several transport layer protocols, ICMP, UDP, and TCP. For ICMP, we use ICMP echo requests and responses, the underlying protocol used by the ping utility. For UDP, we use HTTP3 over QUIC, which itself runs over UDP. And for TCP, we use several application protocols such as HTTP1 and SSH. Going back to the attack scenarios, in the firewall piercing scenario, the pivot host is the firewall itself. It may run on a Linux operating system or perhaps OpenBSD. We construct a covert channel wherein the sender on the internal isolated network communicates with the firewall itself, for example, pinging it over ICMP, and likewise the receiver on the internet also communicates with the firewall by pinging it. The covert channel then allows the sender to send bits to the receiver. In a firewall subversion scenario, the pivot host is the DMZ server, which may be a macOS server exposing an external application over QUIC to the internet, for example, a production application, and an internal application over QUIC to the isolated network, for example, the staging environment for the application's next version. Again, the sender and receiver establish a covert channel through this DMZ host, even though they access different applications and different ports. In the firewall subversion via containers, the pivot host is a Linux operating system that runs two isolated containers, an internal container and an external third-party container. Although the two containers are not communicating with each other, the sender and receiver can construct a covert channel through the internal state of the underlying host and thus communicate. Finally, in the host alias detection scenario, the attacker uses the covert channel approach in a different way. The attacker implements both the sender and receiver from the internet vantage point. The sender is implemented with the first virtual network service as its pivot host, while the receiver is implemented with the second virtual network service as its pivot host. If the two virtual network services share the same underlying host, same kernel, then a covert channel will be successfully constructed between the sender and receiver. Otherwise, a covert channel will not be constructed. The internal state exploited in this research, the internal states exploited in this research are an IPv4 ID internal state, which guarantees non-repetition period on Linux for connectionless transport protocols such as UDP and ICMP, for Windows, for macOS, and in this new kernel in general, also for connectionless transport protocols, and for OpenBSD. A TCP ISN internal state that guarantees monotonicity period was exploited on NetBSD. It's not covered in today's presentation. And likewise, an IPv6 flow label internal state which guarantees non-repetition period on NetBSD, and again, not covered in today's presentation. Now I will explain how each internal protocol state can be turned into a covert channel. We start with the Linux kernel IPv4 ID implementation for connectionless transport protocols such as UDP and ICMP. It is built upon a table of 2048 counters, shown here as beta. The algorithm hashes the destination IP address of the soon-to-be-sent packet as an index to the table, increments the counter by 1, and also adds a small amount of random noise up to the amount of time elapsed since the previous access of this counter. The amount of time is measured in 4 millisecond units. The key observation that allows us to attack the algorithm is that if both the sender IP and the receiver IP addresses hashes collide, then, that is, they both generate the same index I and fall into the same counter beta I, then when the kernel sends back packets to the sender and to the receiver, the packet's IPv4 ID will be generated using the same counter. This means that the receiver can observe whether the kernel sent packets to the sender by measuring the difference in the IPv4 ID that the receiver observes. In order to overcome the random noise, the sender must send packets quickly enough so that the rate of IPv4 ID increments overshadows the possible random noise introduced by the algorithm itself. To mount the attack, the sender must be able to spoof multiple IP addresses. In this example, the sender can spoof 100 IP addresses from the isolated network. It is also assumed that the sender can interact with the pivot host, for example, to sending ICMP echo requests, also known as pings, or QUIC requests over UDP. The receiver is assumed to control multiple IP addresses. In this example, we assume the receiver controls 140 IP addresses on the internet. The receiver is assumed to be able to interact with the pivot host and receive packets from it, for example, by sending it ICMP echo requests or QUIC initial requests to HTTP3 open port. This protocol may be different than the one used by the sender. Our choice of 100 IP addresses spoofed by the sender and 140 IP addresses owned by the receiver ensures that with probability around 99.9%, there will be at least one sender IP and one receiver IP whose hashes collide. To send a single bit at a given time slot, the receiver polls the pivot host from all 140 receiver IP addresses at 10 millisecond intervals during the entire time slot and records the IPv4 ID. To signal the bit 1, the sender sends a burst of 20 requests during 10 milliseconds from each of its spoofed 100 IP addresses to the pivot host. The time it takes the sender to do so defines the time slot. To signal the bit 0, the sender does nothing. At the end of the time slot, the receiver checks if any two consecutive samples of IPv4 ID on any of its IP addresses had an increment above 10. This is interpreted as the bit 1. If all increments are below 5, or a bit more allowing for some noise, then the bit is deemed to be 0. As for Windows, we reverse engineered the Windows Server code that manages IPv4 ID generation. We discovered that the Windows Server keeps IPv4 ID in an object called path, which has an instance per source and destination IP combination. When a new path object is added, its IPv4 ID is initialized with a random value. When sending packets using an existing path object, the IPv4 ID is simply incremented. Since the set of path objects can be allowed to grow indefinitely, there is a procedure for path object removal. This procedure is triggered either by the number of path objects exceeding some threshold, 32K objects, or by flood detection, which is the insertion of 5,000 new path objects during half a second. The removal itself goes over the path objects and removes stale ones path objects that were not accessed in the last 60 seconds. The scan proceeds at a rate of 2000 path objects per second. Our key observation here is that if a receiver sees a disruption in the IPv4 ID of an old, stale connection, then the receiver knows that the original path object was removed. To turn this into a covert channel, at time t equals 0, the receiver polls the pivot host, for example sending a QUIC request and receiving a QUIC response. At time t equals 60 seconds, to signal the bit 1, the sender floods the pivot host from spoofed 10,000 IP addresses during half a second. This is needed because the sender doesn't know the exact timing of half seconds on the pivot host. The pivot host then initiates the procedure for removal of stale path objects and takes 10 seconds to go over all path objects. During this phase, the pivot host also removes the receiver's path object because it's stale. In contrast, for bit 0, the sender does nothing, and the receiver's path object remains intact. Finally, at time t equals 71 seconds, the receiver polls the pivot host again. If the IPv4 ID is incremented by 1, then the bit is deemed to be 0. Otherwise, IPv4 ID appears to be random, and the bit is deemed to be 1. In macOS, more precisely the GNU kernel, but only for connectionless transport protocols such as ICMP and UDP, and for OpenBSD, both operating systems, the IPv4 ID generation algorithm is similar. The kernel keeps a list of M most recently used IPv4 IDs. This is done globally, not per IP address. For macOS, M equals 4K, and for OpenBSD, M equals 32K. The kernel picks an IPv4 ID at random from the remaining 64K minus M values. Then the kernel pushes this newly used value to the top of the list and pops the oldest value. Our observation here is that within a run of M consecutive packets, if we look at two distinct batches of 1000 packets, they will have 0 collisions since the non-repeat period is M. In contrast, if we look at two distinct batches of 10,000 packets, but more than M packets apart, then these will have an average of around 15 collisions. We can turn this into a covert channel, sending 1 bit at a time slot. For this, the receiver polls 1000 IPv4 IDs, for example, download a large file over QUIC. To signal the bit 1, the sender makes the pivot host send M messages. To signal the bit 0, the sender does nothing. Finally, the receiver polls another 1000 IPv4 IDs again. If there are collisions, the bit is 1. If there are no collisions, the bit is 0. As you can see in this table, we managed to come up with many covert channels implementations against multiple operating systems, Linux, Windows, macOS, OpenBSD, and NetBSD, and using multiple protocol header fields, and over many common transport protocols, UDP, ICMP, and TCP. Our attack bandwidth depends on the particular protocol and operating system combinations, and varies from 7,200 bits per hour to 41 bits per hour. While this rate is not sufficient for exfiltration of gigabytes of information, it can be very useful for scenarios that require exfiltration of small strategic data, such as cryptographic keys, certificates, and compressed critical information. To summarize, we demonstrated new information leaks in present-day operating system implementations of IPv4 ID, flow label, and TCP ISM. We explained how they can be turned into covert channels, and we described new attack scenarios targeting firewalled and isolated networks, firewall piercing, firewall subversion via DMZ pivot host, and firewall subversion via core resident containers. Thus, we recommend that the protocol header fields in question be populated with completely random bits, which is what macOS and the GNU kernel in general and NetBSD do for IPv4 ID following our disclosure. For better isolation, we recommend that isolated networks be prevented from directly accessing DMZ hosts and internet-facing firewalls and routers. Finally, we recommend not to rely on containers for isolation. As can be seen at the bottom of this slide, Linux, Apple, and NetBSD released fixes for the issues that we reported to them. Thank you for attending my presentation. If there are any questions, I will be happy to field them now.